Hey, alrighty, it's time to get started now. So we were last time we were doing this example. We were looking at this example on the unit ball, trying to find a triple integral on the unit ball. And how do we rewrite this triple? So how do we rewrite this triple integral on unit ball as an iterated integral? If we made an arbitrary choice, no particular reason to do the slicing in this order. Of course, it doesn't matter, right? In this case, the sphere is highly symmetric. You can probably do it in any order. It's about the same difficulty in either order. First thing we argued is looking at this picture, that in the process of doing the x slicing, the outside slicing, the first slice is over here. X is clearly -1, right? It's a sphere of radius 1. So that's clear. Last slice, where x is equal to +1. Again, pretty clear. And here's what a generic x slice looks like. Okay, so now for the purposes of the next integral, the second integral, we're going to focus our attention on this slice, right? So we're not don't care about stuff happening over here, right? These points we'll get those for other values of x. We're going to focus on one value of x, this being that value of x, and we want to consider the range of values of y and z on that x slice. Okay, so on that x slice, this is about where we left off. This is what z slices look like. Right, taking this x slice and doing z slices. Looks something kind of like this. First slice is down here. Last slice is right there. And we want to know what are the values of z that correspond to those slices. Okay, so said differently, then what we want to know is what are the values of z that correspond to these 2 points. So we've got to write down what we know about these 2 points. So let's take these one at a time. We'll start with the top one. By the way, you can probably see there's a lot of symmetry going on here. So the top z bound is going to be the negative of the bottom z bound, vice versa. Okay, so this point, what do we know about this point? Well, for one thing, that point is on the sphere, right? And the sphere has an equation that we can write down: x squared plus y squared plus z squared is equal to 1. What else do we know about that point? Well, we know what x is, right? We've already agreed that we're looking on a certain x slice. So this is, as y'all recall, what I like to represent in a little sloppy notation as, well, x is what it is, so I write x equal to x. A little bit silly. Okay, so there's one more thing that we know, though, about this point that we really need in order to be able to solve for what we're interested in, and that is we know by the symmetries of the sphere that this point is in the xz plane, right? We know that y is equal to 0, and we really need the picture to be able to draw that conclusion, right? At minimum, we need to have a geometric understanding of the nature of this shape to come to that realization. Okay. So I'm a big believer in having a picture. It's a lot easier to have a picture and use to let your geometric intuition have the advantage of a picture to work with instead of having to figure all this out, see all these symmetries in your head. So anyway, y equals 0. And with all that in mind, we keep in mind that what we're actually interested in is z. Right? So we're going to solve for z in this equation. And with the understanding that, with the understanding that y is equal to 0, you take this, plug it in there, the y goes away. X is what it is. We can leave the x's. They're not a problem. And z is plus or minus square root of 1 minus x squared. Everybody happy? Any questions? Okay. All right. So that goes back to our bounds here. Remember, we've already agreed that x goes from -1 to 1. And now, I guess I'll zoom in so we can see what's going on here. Now we see that z goes from negative square root of 1 minus x squared to positive. Okay, so it's the same process that we've seen in one other example, I guess, before this one, and it's just a different geometry, right? You get different algebra correspondingly, but notice that you really need to have the picture in order to be able to figure out what is the relevant algebra from which you should work algebraically. Okay, now of course we're not done yet. It remains we've got to figure out what's the range of values of y. So for the given x that we fixed, for now an arbitrary z that we're going to fix for that given x. So on a z slice of our x slice, we want to know what's the range of values of y. So going back to our picture, there's our x slice. Now, we did all this work. Get rid of that. We are now going to focus our attention on, within this x slice, here is a arbitrary z slice. And on that z slice, I want to know what's the range of values of y. So we're going to look at, this point and that point, and we want to know their y coordinates. Okay. And I have a better picture already drawn here, so let's look at this point. So x is fixed, z is fixed. We know x. We know z. We're looking now at that point. What's its y coordinate? That point. What's its y coordinate? So again, what do we know about these things? Well, I know that these points are both on the sphere, and I know the x's and I know the z's. And so the algebra on this one is pretty straightforward, really. We have x squared plus y squared plus z squared is equal to 1. Solve for y, given that x and z are both known, and y is plus or minus the square root of 1 minus x squared minus z squared. Yeah. Everybody happy with that? Same process, really, right? Just different geometry. Okay. Alrighty, so that gives us our final bounds, which, let's see, I guess are back here. Yeah, right, so our y bounds from there to there. Now, is this a desirable integral to compute? Very much not. Right? Let's imagine the nightmare that it would be to compute this integral. We have to do an antiderivative with respect to y of whatever our integrand is. Fine, that might be harmless. I mean, I don't know what f is, but let's assume f is relatively harmless. That'd be fine, but then I'm going to plug in these two ugly expressions wherever y appears in that antiderivative. That means that when I get around to doing this integral, let's see, I think I used blue for the x, not for the z integral. In this z integral, I'm going to have a great big expression involving square root of 1 minus x squared minus z squared that I'll have to do a z antiderivative of. That's going to be algebraically brutal. Possible. There's a lot of potential for undesirable there. And if I were to be able to make it through that integration, I would then be plugging in place of z more square roots. Right? So, yikes. So we're going to have a potentially horrendous expression of x that I'm going to have to do an x antiderivative of. So this looks like a nightmare of inconvenience, and I'm going to plant a thought. Wouldn't it be nice if we could come up with a different way to deal with this kind of an integral here instead of doing it, slicing it in this way? Is there some other way we can get around to computing that? And the answer is going to be yes. We won't get to it today, but we're going to get to part of that answer today. Okay. So I just wanted to plant a thought there. Okay, so let's see here. Another example. Where did I start the text on this next example? Yeah, okay, here we go. Okay, so another triple integral. Again, why are we computing this triple integral? I don't know, maybe we're computing a mass, and so we're doing a triple integral of density. Maybe we're computing a number of bacteria, so we're doing a triple integral of bacteria population density. Maybe we're computing quantity of pollution, and we're doing a triple integral of concentration. Whatever, right? So the first part of the problem of turn the application into a triple integral, let's say that's been done. We want to focus on how do I turn this triple integral over this region D into an iterated integral or nested integral. Okay, so our region D is bounded between. There's that language again. So we have a geometry task of looking at these surfaces, figuring out what we've got. And we have these two paraboloids, z equals 2x squared plus 2y squared, and, or I'll use a different color, z equals 1 plus x squared plus y squared. And let's draw these two paraboloids. Right, so here's z equals 1 plus x squared plus y squared. Here's a steeper but starting lower paraboloid. Right, so remember, think back to chapter 2, and both of these are rotationally symmetric. They have parabolic cross sections, but they're different vertex, different sort of steepness. So this is what these two bowls look like. Make sure that you can do that. Right, make sure you're comfortable with looking at these equations and deducing what kind of surfaces these are, being able to draw them reasonably well. And then, artistically, how do you represent this? I mean, this is always hard. How do you represent some odd-shaped solid? This is what I've done here. It's far from perfect, but I think it's reasonably effective and reasonably easy to execute. So, you might consider, how you go about drawing these kinds of things. And you notice I use dotted lines in here. To represent the this part of the top surface, which is kind of obscured. You can't really see that part of the top surface because it's sort of inside of the bowl or whatever you want to call this thing, right? So that's the little dotted lines which suggest that. Not hard to persuade yourself as well that they intersect up here. You can write down some algebra, figure out where that is, what's the radius of that circle, etc. Okay, so let's talk about how to slice this up. Right? Now, you have 6 choices. The examples that we've seen so far, it kind of didn't matter. Spheres are super symmetric. The tetrahedron that we looked at was really symmetric in a lot of ways. So in those cases, it didn't matter. Here, it's going to matter quite a bit. So we're going to try to anticipate this without going through the trouble of actually, doing all of the actual slicing. And the first observation I want to make is, let's not do our DZ slicing first. Let's not do DZ on the outside. So if we were to do DZ slicing on the outside, at a first glance, you might think, okay, well, it's not that bad. Here's what one of those slices looks like. It would be a disc. Seems relatively harmless, right? Until you realize that that's only because I, arbitrarily chose to draw a slice for that value of z. What about other values of z? At higher values of z, like up here, well, we're kind of slicing through the bowl part. We're not slicing through the base, if you will. We're slicing through the bowl part of this thing, and the slice is going to have a kind of a hole in it. The slice at that height would be maybe kind of like that. It'd be an annulus, they call it. So, I mean, okay, fine. It's not that you can't do that. But the algebra becomes different. And so certainly we're going to have to deal with one z integral from there to there, and then a completely different z integral from there to there. So we're going to have at least 2 different integrals. So we already don't like it, right? But it's worse than that. Notice that when you get to this annulus then, right, you start slicing up this annulus. What do slices of this annulus look like as you slice, let's say, perpendicular to the y-axis? Maybe we do our y slicing next. Our y slices would look like this for a while until I hit the inner circle, and then the slices would start to look different. I'd have these kinds of slices over there, and I'd have these kinds of slices over here. And then after I finish with that, it would go back to looking kind of like it had at the start, but again, in a different chunk. So doing an integral over this green z-slice would require 4 separate integrals. That's 4 separate integrals inside of one of the already 2 integrals. So it would be a total of 5 integrals. This is highly undesirable. Right? Is everybody on board? Does everybody see why we definitely don't want to do this? So, how do you see this coming in advance? Well, try not to slice through some sort of an abrupt change in the shape of something. So we talked about corners. Don't slice through corners mid-process. Right? So along those same lines, the moral I'm going to say here is don't slice through don't sideswipe slice through a surface. Right? Because the surfaces below that and the surfaces above that, the slices above and below that are going to look qualitatively different and give you different integrals. So, just highly undesirable. So let's just take a pause or a pass on that completely. Oh, I already had a picture. Right? Okay. So here's a different point of view I'm going to give you. I'm going to slice, X and Y first, and we'll put DZ on the inside. Let me write that down. So we're going to do DZ on the inside and then DX, DY on the outside. There's our order. And before I get into details, I want to draw some pictures of what do the Y and then X slices look like as I go through this solid. Okay, well, you'll notice here's our solid. I've already got that drawn. There's our solid. And you'll notice that I'm also drawing, for reasons that I'll mention momentarily, I've drawn the shadow of our solid down here in the XY plane. Okay. And here we go. Let's start doing our slices. As I slice perpendicular to the Y-axis, my Y slices, ooh, boy, artistic challenge. My Y slices are going to look kind of like, ooh, man, kind of like that, maybe. Right? Everybody kind of see that coming? So, when you slice a paraboloid, the slices are parabolas, and so the top parabola will slice to give me that. So the top paraboloid will slice to give me that parabola. And the bottom paraboloid might slice to give me that parabola. And two parabolas, what's between the two parabolas will be this green thing. So there's what one of my Y slices look like. Really hard to draw. I could probably live with this drawing, but it's certainly not great, and it's not something I'd really like to do. It looks annoying. Here's the observation I want to make about this slice. There it is. The range of values, though, if you think about it, this Y slice, if in this slicing process, if I also think about how did that slice up the projection down here, do a better job of that. Right, the range of values of Y over the solid, well, it starts there and ends kind of there. Below which, as you slice up the projection, starts there and ends there. Right? For every slice of the solid, there's a corresponding slice of the projection. So the starting value on the solid of Y is going to be the same as the starting value of Y on the projection. Ditto for the ending values. So, since what I really needed in my Y slicing process is to know what's the range of values of Y, I can figure out this range of values of Y, what goes here and what goes here by ignoring what's happening up there. I mean, what's happening up there is hard to understand, but just observing that there's my first Y slice and there's my last Y slice on the projection. That will let me get those Y bounds. Yeah? Everybody happy with that? So feel free to look at the projection instead of looking at the actual solid. It's a great trick. It'll save you lots of trouble with drawing what can be pretty darn challenging figures, right? When you're taking these, looking at trying to draw a three-dimensional solid and slices at various angles, it's very difficult. Okay, so likewise with the X slices. Now let me draw, again, one of our Y slices. Okay, so again, very hard to do, but roughly speaking, that's what one of my Y slices looks like. This is the corresponding slice of the in the projection. Now let's talk about the range of values of x. X, you could say it starts here and then the slices look like that and then ends there. But again, the slice of the projection is exactly the projection of the slice. Everything that's in the solid, its shadow is directly below. It has all the same x and y coordinates. When you project, all you do is ignore z. Throwing away z doesn't change x and y. And so I could instead just look at what are the starting and ending values of x on the projection. Right? So I think this is a great trick. To find the bounds, let me just summarize here. To find the bounds, on the x and y integrals, specifically those being the outside, the two furthest to the outside integrals. Whatever those two furthest to the outside integrals are, x and y in this case, you can just look at the projection down to that coordinate plane, right? Projection down to the xy plane, and just think about, well, the solid's hard. I don't want to think about the solid, but let's look at this projection. It's nice and easy. What's the range of values of x and y on that projection? This becomes a two-dimensional problem instead of a three-dimensional problem. Yeah?
Do we need any sort of justification to jump from solid projection, or is it
No, because the way I'm presenting this as is that this is something you're allowed to do. This is a given trick for this course. Yeah, so you can you want to say on an exam solution, you want to say looking at the projection, and then just go ahead. Yeah, right. Right. So the projection's real easy to write down. Again, it's I'm going to draw it to look ahead on just because it's easier to draw that way, and it's a circle. And we've talked about the range of values of x and y on circles. That's a double integral question, really. Get right down to it. Right. So that gives you your x and y bounds. So the nice thing about it is, as hard as this geometric challenge is to draw, you can come up with the x and y bounds. You can get 2/3 of the way there simply by looking at its two-dimensional projection into the xy plane, and that gives us that the x and y bounds are these. Everybody happy with the trick? I'm a big fan. Okay, so something to keep in mind. Now, okay, it does remain that we've got to figure out the at the very last here, we've got to figure out, well, what are the z bounds? So for a given x, for a given y, what's the range of values of z? The projection trick does not work for this. It only works for sort of, what's furthest to the outside. So here we do have to focus our attention on, okay, for a given x, for a given y, x and y being fixed, and then we got to look at the actual solid. So here we are. Here's a particular x and a particular y, and for that particular x and particular y, there's our x slice of our y slice, and I want to know the range of values of z. So this point tells me the lower bound for z. This point tells me the upper bound for z. Conveniently, those points are on surfaces for which we already know the equations. Solve for z. Oh, conveniently, those z's have already been solved for, right? And so those bounds are easy to find. So these bounds here are going to come straight from these equations. So that's one of them, and that's the other. Do keep in mind which surface is on top and which surface is on the bottom, and the integral ends up to be this. So again, the x and y bounds came from the projection, looking at the projection, and then the z bounds came from looking at the solid. Yeah? Good? Okay, last triple integral example I want to show you. A little bit tricky, but I think there's a lot of value in this specific example. A couple of neat lessons in this example. Our solid is defined in a very non-obvious way. We're looking at a solid region D that's bounded by 5 planes. Z equals 0, z equals x, z equals 2 minus x, y equals 0, y equals 3 minus z. Now, before I get into this, I want to tell you why, one of the reasons why I like this example. and that is to address what a lot of students think they can do or think they can kind of get away with when it comes to writing down iterated integrals. And that is, a lot of students think that they can sort of, you can kind of see this coming from the algebra. Right? You look at the algebra that was given in this previous example, and in the previous example, well, I mean, my gosh, the z-bounds were just downright given in the algebra. Can't I just copy? Right? It's said in the statement of the question, z equals 1 plus x squared plus y squared. Why can't I just transcribe that on into there? And then, I mean, they're parabolas, so, they're going to, paraboloids intersect in disks. It's not hard to persuade yourself maybe that it's, in some sense, maybe kind of obvious that these are the x and y bounds. And I want to persuade you that this strategy of, I'm going to look at the algebra that I'm given. Let's see here. Where's the, it was way back here. Wow. Okay, the weird page. That I'm going to look at the algebra that I'm given, and I don't need to draw a picture. I can just deduce from the algebra what the bounds for the integral are going to be. I want to persuade you that that is a losing strategy. That is absolutely unacceptable, and it really doesn't make any sense. I mean, again, you might get lucky sometimes. You might even get lucky a surprisingly high percentage of the time, but it is not a mathematically legitimate argument when, of course, is what we're actually interested in, right? So here's my argument for why you just cannot count on that. It's this example. Here, take these 5 planes. What's the right answer? Right, it's really not obvious. Can you just insist that, well, I guess z goes from x to 2 minus x? Oh, no, wait. Does z go from 0 to 2 minus x? Does z go from 0 to x? Do I solve for z in that last equation? Maybe z goes from 0 to 3 minus y? It is very, very far from clear which ones of these equations are playing what role in the eventual iterated integrals. Does everybody see what I'm talking about? Completely cryptic. So I'm just going to look at the algebra and, make educated guesses or, guesses based on experiences. Which ones are going to participate in what bounds? Forget it. Not going to work. Okay. So the other reason I like this example is as an excuse to talk about a neat method for understanding what solids look like, and I think is useful. So I want to point out that these first 3 planes, z equals 0, z equals x, and z equals 2 minus x, all have a common and important shared feature in that their equations have no y's in them. All right. So I propose, if you think about it, if an equation does not have the variable y in it, that means that if you have some point on that surface, if you change the y coordinate, that doesn't affect the equation anyway. Therefore, if you have a point on the surface and you change the y coordinate, the resulting point is also on the same surface. Or said differently, these surfaces, by not having y in them, have to be parallel to the y-axis. Right? Now, a different point of view you can take is you could take a chapter 1 point of view and say, okay, well, if there's no y's in the equation, these are the equations of planes. You can deduce from that what the normal vector looks like. The normal vector does not have a component in the y direction, and what does that mean about the plane? The punchline is, and that's a healthy exercise to think through, the punchline is these are planes parallel to the y-axis. Okay, so if you want to draw something parallel to the y-axis, you can simply understand what they look like in the xz plane. Right? In the xz plane, there's what z equals 0 looks like. There's what z equals x looks like. There's what x plus z equals 2 looks like. Those 3 planes intersection with the xz plane are easy. It makes a triangle. Right? And since we know that these planes are parallel to the y-axis, we can deduce how they intersect by just dragging this triangle parallel to the y-axis. Right? And so we get this big prism. All right. So I think this is a really valuable trick. I mean, again, if you look at this list of 5 planes, it's real hard to figure out where to even start. Excuse me. In fact, if these 5 planes were just 5 random planes, this would be a very difficult geometry problem of drawing all 5 planes and looking at this there's all these planes. How do they intersect? What kind of a shape does this make? That's a tough one, right? And we are now 60% of the way done with the problem after making this one clever observation about, hey, there's no y's in the first three equations. Everybody on board with that trick? It's a big trouble saver. Okay. All right, so the last two equations, well, I mean, we know most of what our solid looks like. The last two equations I can just kind of add on one at a time. Y equals 0 is an easy plane. Let's come up here and draw y equals 0. Y equals 0 is the xz plane. How does the xz plane interact with this, this prism that I have going here? Not hard to persuade you that it intersects by kind of slicing through there. So that's going to make a face on this thing. And then let's see the other one. The last plane is y equals 3 minus z, or let me rewrite that as color. Y plus z equals 3, if you prefer. What's that look like? Y plus z equals 3. Well, hey, no x's. All right, so this is a plane parallel to the x-axis. And if I want to understand this plane parallel to the x-axis, I can simply draw it in the yz plane. Let's draw y plus z equals 3 in the yz plane. I know that the actual plane I'm interested in is what I get when I drag this parallel to the x-axis. And now you really do have to think about this three-dimensionally. I argue that what we have here is a prism that's being cut at a diagonal. Right? And cutting it at a diagonal, the resulting cross section is going to be it's not going to be straight up and down like this. This point isn't going to be there; it's going to be over here. So it's going to look kind of like that. How we doing? Everybody on board? Okay, so let me get rid of it. So that's not that. Okay, so it looks like that. Okay, so now our picture has got a lot of stuff going on it that we no longer need. All this green for the parts of the prism that are no longer there because they got chopped off, I can throw them away. All I really need left over is this. Right, that's what I've got in yellow there, what our solid actually looks like. So now I've got this convenient little stylus and I can erase strokes and all that kind of stuff. You can't do that on paper. But what you can do is take a figure and, like I've talked about before, learn from what you've drawn. Go ahead and make your figure, work stuff out, draw stuff that shouldn't be there. Use the pencil as a tool for helping you understand what the shape looks like. And then once you understand what the shape looks like, draw it over. Right, and make an actually good figure representing what you really want to know, which is this thing. All right, is everybody on board? So that was kind of an exploration in math drawing that I think is worthwhile. I wanted y'all to see. Okay, all right. So here's our solid now, and I emphasize that's a pretty significant part of the problem here is figuring out what does this intersection of five planes, or the region bounded by these five planes, what does it even look like? It's part of the problem. Okay. And this course is unavoidably geometric, and this is a great example. Okay, so the next part of the question is, okay, so I'm going to make an integral over this solid, again, for whatever reason. Maybe I'm computing mass, whatever. How am I going to slice this up? And this is another example where you really have to think it through which order you're going to slice. If you slice in certain directions, bad things happen. But if you make clever choices about which way to slice, then bad things don't happen. Okay, so for example, let's start off by slicing first perpendicular to the x-axis. What do x slices look like? Well, an x slice over at the beginning looks like that, and then an x slice a little bit later on looks like that, and you can keep going, but eventually you're going to hit that corner. So slicing in the x direction, you're going to hit a corner. The problem of which is that for these values of x, it's this plane that gives you the top edge of the resulting slice. Whereas for these other values of x over here, right? It's not. It's this plane that gives you the top edge of the resulting slice. Right? So as we saw before with double integrals, try not to slice through corners, or as you might say differently in this example, try not to slice through edges in that way, because it's going to require you to write multiple iterated integrals to be able to get through the whole thing. Okay, so we don't want to slice first perpendicular to the x-axis. Bad things happen. Now, what about if we go first perpendicular to the y-axis? Well, okay, so here's what our slices look like. And, you don't have to draw these necessarily, but it, kind of helps to draw some of those slices. And notice that eventually you hit this corner, after which the slices look different. Right? And so again, you're going to have to use a second, you're going to have at least 2 iterated integrals if you insist on doing your y slicing on the outside. Everybody sold on that? Okay, so we're 0 for 2 on attempts. Now let's take a third attempt. Let's try perpendicular to the z-axis first. Z slices look like that. And then that. And then that, and then the last one is up there, and we're done. We didn't slice through any corners. There's no reason to sort of start over with a new iterated integral. I mean, these are qualitatively all the same kinds of slices, and so this makes it look like we can get through the whole thing with one iterated integral. Yeah? Everybody happy? So we definitely want to do our dz slicing on the outside. And then now we have a remaining question of what order should we do the x and the y on any one of these slices? Okay, and I think I may already have yeah, here we go. Okay, so z, this first z slice, z is clearly 0. The last slice. Now here you got to do a little bit of algebra. Right? Where is that last slice? Well, you've got to think about the fact that this equation here is x plus z equals 2. And this equation here is x equals z. You got to write down those equations and then solve for what you're interested in, and what you'll find is that you get 1. Okay, so again, importantly, you got to identify, what's a point that defines what I'm interested in? Geometrically, what do I know about that point? Algebraically, what do I know about that geometry? And then solve for what you want. All right. Okay, next, what do we do? This resulting z slice. Do I slice first perpendicular to the x-axis or first perpendicular to the z-axis? And it turns out it doesn't really matter, because here's what y slices would look like. No problem. Right? Here's what x slices would look like. I guess I'm going backwards, but anyway, whatever, no problem. It's a rectangular slice, so there's no issue there. Either order you want. Everybody happy with that? I will point out that you might not get so lucky. Here's a variation of this question. Let's suppose that this plane here, let's suppose that instead of y plus z equals 3, what if that had instead been, what if it had been x plus y plus z equals 3? Well, then it wouldn't slice through parallel to the x-axis. Now x is in the equation. This plane is not parallel to the x-axis. This would look something more like that. Therefore, my solid, harder to draw among other things, but my solid would look like this. And then my z would look like that. Everybody see what would happen there? Again, hypothetically, if there had been an extra x in that equation there. So this is what my z-slice would look like. And now we really got to pay attention about, how to slice up this slice. This slice, I didn't draw it very well, did I? That slice, it's fine to slice this up perpendicular to the x-axis. But it's not fine to slice perpendicular to the y-axis. If you slice perpendicular to the y-axis, you're going to hit this corner. Right? And then you'll have a completely different slicing over there beyond that. So, what answers that question for you? What in this hypothetical, variation of this question, what tells you which order to do the differentials? The picture, right? The algebra would really not make that clear. Think about how would you make the decision looking at this algebra that if this had been x plus y equals 3 minus z, how would it be clear that, so we clearly have to do our dz slicing first, and then after that we have to do, x and then y. That's not at all visible from the algebra. Everybody on board? Okay, so punchline. How does this affect you guys? On an exam, keep in mind, right? So one of the fundamental perspectives in this class is this is not a class about answers, whether your answer is right or wrong, right? It's a question about, do you explain reasoning? I'm interested in your reasoning and your thought process, right? So any thought process on how to slice up a three-dimensional solid and get a resulting nested integral, I need to see the geometry of that. I need to see the picture that you draw, right? And in other words, you can't just write it down. Well, it was right. I did it in my head. I didn't need to write it down. No, you have to write it down because I need to know. I need evidence that you're making legitimate reasoning based on understanding what the picture looks like, right? And not that you're making sort of educated guesses based on just the algebraic statement of the question and maybe you just got lucky, right? I need to distinguish between those. So always give me a picture. That is a required part of the problems, is to give me a picture so I can understand what your geometric reasoning was. Okay. Right, so moving along. Okay, so that finishes triple integrals, bunch of exercises. By the way, a reminder, in these exercises there are some artistic challenges. Drawing these things is non-trivial. If you're not very good at drawing things, come to office hours. Right, I'll give you my little 10-minute spiel on basics of making decent drawings. Of three-dimensional figures in this kind of context. Anyway, so if that's something that you think you might need help on, come talk to me. Okay. So change of variables. This is a really powerful technique for computing integrals. In some sense, we already know how to compute integrals, right? If you have a double integral, if you have a triple integral, you rewrite it as a nested integral, and then you crank out the fundamental theorem of calculus. And we've seen that sometimes that's a huge pain. Sometimes this is highly undesirable. And what very often makes it undesirable is that the shape of the domain gives rise to bounds that might have square roots in them, or arc cosines, or who knows what. Right? That all comes from the shape of the domain. So sometimes we're doing integrals on domains that we don't like, that we really, really importantly don't like. It's making the problem intractable. Okay. So the question I want to propose is, how can we turn an integral over one domain into an integral over a different domain? Wouldn't that be nice if we could change the domain? Okay, so I propose y'all have actually seen an example of this previously. You obviously didn't think of it in this way in a Calc 1 class, but here's the substitution rule, what's commonly referred to as the substitution rule. Well, I'll say this. This is called the substitution rule for antiderivatives, and this is the substitution rule for integrals. All right, so hope that looks familiar. All this said, the way you think about this in a Calc 1 class is, well, look, if x is equal to g of t, then dx is g prime of t dt, and then the case gets made that, all right, well, just take your dx and write it as g prime of t dt. And everywhere you see an x, right, is g of t. Right, now that's a kind of an algebraic hand waving, right? But anyway, this is how kind of business is done in Calc 1 class. So anyway, I hope that looks familiar. Okay, do notice though, very importantly, that the bounds have changed. Right, now this, the way they justify this in a Calc 1, there's different ways to justify this in a Calc 1 class, but while t was going from a to b, x is not. X goes from g of a to g of b. And again, the different cases can be made. I want to show you a certain point of view on how to think about this rule. Again, not because I'm trying to solidify your Calc 1, right? I'm going to assume you're, in some cases, yes, but not in this case. Right now, the reason I want to take a certain specific point of view on this is because, like with derivatives, like with integrals, the specific point of view that I'm going to take is the specific point of view that will allow me to generalize to a higher dimensional context. Right? So this is laying groundwork for a sort of a two-dimensional version and then a three-dimensional version of kind of the same idea. So here's the idea. We wrote down, let's see here, x equals g of t. Let's draw a picture of that. Here we go. There's x is equal to g of t. All right? X is g of t. So we can think of that as saying that we've got this function that takes us from the t-axis to the x-axis, and I make the observation that, well, that means that if I have some interval over here on the t-axis, everything just pushes forward, and there is a corresponding image interval over here on the x-axis. Okay? Let me further note that if I were to take this interval on the t-axis, and if I were to do what we typically do on intervals on the x-axis and chop it up, right? This is our slicing process. Imagine we're interested in integrals. Well, we slice that up, and we slice it up in this very special way. We, even slices, delta t equals b minus a over n, all that, typical stuff. Then I get this, what we call a partition of this interval. And let me just observe that if I take that partition, if I take every one of these values, plug it into the function, I get a corresponding image partition point over here. And the punchline is that a partitioning of this interval on the t-axis gives me a different partition on the x-axis. So I'm just laying groundwork. I haven't really done anything yet. Now, you might gripe, understandably, that, hey, this was a regular partition. All the pieces were the same size, and over here, these aren't. So one thing we did not talk about previously when we were talking about integrals, right? Remember, we've defined integrals, different kinds of integrals. I always did my Riemann sums in such a way that the slicing was even. And the reason I did that was laziness. There's no real reason that the slices have to all be the same size. It's just so much easier to write down delta x equals b minus a over n. It's very convenient. And it turns out for continuous functions it doesn't matter anyway. Right? So I took the easiest possible definition of Riemann sums at that time. So I'm going to assert here, and again this is not an analysis class, so I'm not going to prove it. I don't want y'all to sweat it, but I'm going to assert and make what I think is a pretty plausible argument that if you're trying to compute the mass of a rod, let's take a one-dimensional rod, or you're trying to compute that mass, and if you argue that the total mass is the sum of the little masses that you slice it up into, who cares if those slices are the same width? Mass is an intrinsically conserved thing. Right, it's an accumulating quantity like we talked about. So as long as you're slicing it so that the pieces get arbitrarily small, it doesn't matter if they're the same size. Okay, so integrals can totally be defined with non-regular partitions. And so, for example, that slice is a little smaller, that slice is a little bigger. I claim, I hope it's reasonable for you to buy that this is okay and doesn't matter. Okay, so here's the question I'm going to propose. If we have an integral defined on this interval on the x-axis. Let's say that I'm interested in an integral from g of a to g of b. Can I rewrite everything in that integral? Can I do what's called a pullback? I'm going to be using that term a little bit, but I'm going to use it anyway. Can I take the integral on the x-axis and pull back and rewrite everything in that x integral in terms of a t integral? And the answer is totally. There's no problem. You just got to write things down. Here's some of the algebra. So here's my integral on the x-axis. It's a Riemann sum. That's just a definition of an integral. Let's look at the objects inside of here. One of the first objects I have is there's this delta x. This delta x here. Now, can I rewrite that delta x somehow? Well, what do I know about this delta x? Can I rewrite delta x in terms of delta t? There's a temptation to say no. There's a temptation to say, look, hey, whoa, no way. Look, the delta t is clearly smaller, or if not smaller, it's clearly different. This g function kind of contorts and stretches things out in some way that it depends on g. So they're not the same thing. So no fair. Right? So fully agreed. Delta x is not the same as delta t. The question, though, is can I rewrite delta x in terms of delta t? And that we can do. And the appeal that I'm going to make is that we understand what derivatives are. If I look at this function g, right, the derivative of g, many interpretations of derivatives, but one of the big interpretations of derivatives is that it's what you multiply by a change in the input to get a change in the output. And notice that's kind of what I'm in the market for right now. I would like to know what can I do to this, what I could view as a change in the value of t. The width of that little subinterval is a change in the value of t. What do I multiply by a change in t to get the corresponding change in x? And g prime is that thing. Right? So from a point of view on derivatives, delta x is g prime times delta t. What do y'all think about that? Is that all right? So here we go. Back down to our Riemann sum. And I'm just going to rewrite delta x as g prime times delta t. And then, just like I did in the earlier perspective I gave you, I'm going to observe that, well, x is, sorry, got ahead of myself. X is g of t. G prime times delta t remains. So I get this. And now I suppose we have to pull a little fast one here. Notice our Riemann sum where we had f times delta x has turned into, well, there's the f and there's the delta x. And the little fast one I have to pull is to simply move the parentheses around a little bit and group like this. And what I have is a new Riemann sum, a new integral. Oh man, I hit the wrong thing. A new Riemann sum, which is summation. There's my new integrand, delta t. And notice I get exactly the substitution rule. This is an integral of that function, dt. Everybody happy with that? So it's a Riemann sum point of view on the substitution rule. Now again, the point of view that you take in a Calc 1 class is this, you plug in and deal with differentials as if that's okay. Which is a harder question than it sounds like. But victimless crime, I like to call it. But anyway, I want you to see geometrically what's going on because we need this geometric point of view in order to make the two-dimensional version of this. Okay, so said differently, I can think of this g prime here as what I like to call a stretching factor. So I had this dx. I needed to rewrite dx in terms of dt. dx and dt are not the same size, right? I mean, absolutely, you can see it in the picture. I mean, g contorts and stretches things out. But the factor by which dt gets stretched out to make dx, that factor is a known thing, namely the derivative. So I'm going to refer to the role that g prime is playing here as being the stretching factor. It's how much a little piece of the t-axis gets kind of stretched out to become a little piece of the x-axis. Okay. All right, and then as I argued previously, x is g of t. Okay, so anyway, that's why the bounds changed. What had been bounds g of a and g of b, they are those bounds because we started off literally doing an integral on the x-axis where those endpoints are g of a and g of b, right? And they turn into, in this direction, they turn into bounds a and b because that's the bounds on the interval that interval came from. Right? So what we've done here is we've figured out a way to view this as a matter of changing the domain. We had an integral on this domain. We have in effect gotten rid of that as our domain, and we now have an integral instead on this other domain. So it's, again, you don't take this point of view in a Calc 1 class, but this is a really nice point of view for our purposes. Change what the domain is. Okay, so moving along. Okay, we're going to do roughly this same thing in a two-dimensional context. Well, let's suppose we're looking at this domain. We're going to try to rip off the strategy that we just used. Here is a hypothetical domain for a double integral. Now, if this were, section 4.3 or whichever one it is, I could say, hey, let's take maybe I want to compute the mass of this thing. Maybe I want to compute the number of, geese flying around in this county, right? Whatever. And I want to, how do I compute that double integral? Well, I could turn it into an iterated integral and look at what the slicing would turn into. This would be a nightmare of inconvenience. You'd have that piece, and then separately that piece, and then, oh, wait a minute, we're also going to hit that corner. So then you would thirdly have this piece, and then finally that piece. We'd have 4 separate pieces. It's a bummer. Highly undesirable. Okay, so to avoid that, here's our question. Can I rip off the above strategy? Can I take an integral that was defined on one domain and rewrite it as an integral on a new domain? Now, notice, in order to do this, in the strategy that I just stole from, that I'm trying to steal from, the way I did this is I viewed my original domain that I don't like, I viewed it as being an image. I viewed it as being the image of a domain that I'm going to, my new integral is going to be in terms of. So as the image of an interval that for whatever reason maybe I do like. Okay. So the key word is, if you want to get rid of a domain, you need to view it as the image of something. So, all right, here we go. I need to figure out how can I view this domain as being the image of a different domain. And now I've drawn here a much more desirable domain. This is a highly unfortunate and undesirable domain that we don't like. And here is a much nicer domain. Nice, pretty little rectangle that I do like. Right? We're going to do the same pullback strategy. I'm going to try to take the stuff that's on the right. I've got some integral on this green domain, and I'm going to try to take everything that's in that integral and rewrite it in terms of what's going on in the blue domain, and thus, hopefully, fingers crossed, end up with an integral in the blue domain, which is a rectangle, which is easy to do, and life is good. Okay, everybody see the strategy? Okay. So, how do we do that? Here, the main thing I need to do is figure out what is the analog of this observation, that a little piece of the t-axis gets stretched out to become a little piece of the x-axis. And I wrote down a formula for how much I have to stretch out the little piece of the t-axis to get the size of the little piece of the x-axis. So how much does this function g stretch things out? So I need to figure out what is my stretching factor in this case. So here we go. I'm going to start with a little subrectangle over here in the UV plane. Little subrectangle, and I would like to know, okay, look, if I apply this function g, that's going to stretch it out in some way, and maybe make it bigger, it might rotate, it might stretch, it might shear. There's all sorts of ways in which this little rectangle might get messed around with, turned into something that's approximately a parallelogram. And by what factor is the blue rectangle's area going to get stretched to become this green parallelogram's area? So I need to find the area stretching factor from blue to green. It ends up being a straightforward calculation. I can't just say multiply by the derivative of g, because that's not how derivatives work. Derivatives don't convert areas to areas. Derivatives in a two-dimensional context convert vectors to vectors. So what I need to do is say, look, this rectangle is defined by these two vectors. They're going to have images by way of the derivative transformation that are these two vectors, and I want to compute the area of the parallelogram defined by those two green vectors. Hey, this picture is really hard to read, isn't it? Let's get rid of this I just need to focus in on what's going on in there and there. Let's magnify those little regions. Here's that picture again. I need to look at, I already forgot the colors I used, purple. Okay, so I need to look at these two vectors that define my starting rectangle. I need to look at their images that define this resulting parallelogram, and I need to compute this area. Right? So finding these green vectors is actually no big deal. I mean, we have exactly the tool for this. The thing that you keep in mind, purple vectors are the purple vector is the input, the green vector is the output. What do you do? Okay, let's see. What do you do to this purple vector to get this green vector? Well, you multiply by the derivative transformation of this function. Right, the derivative transformation applies to input vectors to give me output vectors. Right? Immediate sort of application of an idea from chapter 4. So this output vector that I'm interested in is computed by that formula. Conveniently, this scalar factor of delta u will factor right out because it's linear transformation. Let's see here. This is a directional derivative where the vector is a standard basis vector. That makes it a partial derivative. So, handy-dandy formula for these edge vectors. That one is defined by that, and that one is computed by that. Just partial derivatives times the delta u and the delta v. So there's my two edge vectors. Y'all remember from chapter 1 how to compute the area of a parallelogram. It's determinate, right? There's a really nice punchline in how the algebra works out here. You take these two vectors. The first one, partial derivatives times delta u. The second one, partial derivatives times delta v. It's a 2 by 2 determinant. Multiply, subtract, the usual formula. And the nice punchline is that the output area relates to the input area by way of multiplication by that factor. So that's exactly what we wanted to find. I wanted to find, how much does area get stretched by computing the output area. I see now that explicitly right there in the formula, this is how much areas get stretched. It's the absolute value of the determinant of the Jacobian matrix. As it turns out, it's a wonderfully convenient formula, and so that's what we call our stretching factor. Let's see, so the stretching factor, and that completes our substitution. What you might want to call a substitution, right? We started off with an integral over this undesirable domain. We don't like that domain. Got a weird shape to it. But it being the image of this pullback domain, I can just plug in what g is Oh, that's a bad color choice. I can plug in what G is, X and Y, or G is U and V. I can just change to this different variable. All I have to do is be careful about what, how I rewrite area in the XY plane. I can't just say XY area is equal to UV area. Of course it's not. It's different. It got all stretched out by this G function. All I really have to do to fix it is insert my stretching factor, which is this Jacobian determinant right there. So it's just like substitutions. Now they don't call it substitutions in the multivariable context, and there's no particular reason why. They call it change of variables, but I mean it kind of means the same thing. If you think about it, you could call substitutions change of variables. It would still make perfect sense. Right? Anyway, for whatever reason, they call this change of variables, and it's a pretty straightforward formula. I mean, if you look at it as a bunch of symbols together, it looks complicated. It looks like, wow, look at all those. Well, that's a lot to memorize, right? All this is saying is if X and Y are functions of U and V, yeah, okay, sure, stick them in there. Just don't forget your stretching factor. There's one thing you have to remember to insert in there to account for the fact that XY areas are not the same as UV areas. If you just make sure to insert your stretching factor, and don't forget what the formula is, it's the absolute value of the Jacobian determinant, go ahead, change your variables. And we have successfully achieved our goal. Remember, our goal was to take an integral that was defined on this domain that we don't like. We hate this domain. It's all curvy and bumpy and corners in weird and unfortunate places. And we have now done the pullback, and we've successfully rewritten it as an integral over this rectangle, right, in terms of U and V. It's a rectangular domain. It's so easy to write that as an iterated integral. And off we go. Okay, so let me show you an example. Yeah, I'll show you an example. Okay. There's a little bit of notation I'm going to come back to. So here's our first example. Let's suppose that for whatever reason we need to compute an integral on that domain. It's pretty undesirable, curvy in weird ways, corners in awkward places. If you were to straight up slice this thing a la section 5.3, it's going to be 3 separate integrals because you're going to hit this corner and you're going to hit this corner, whichever way you slice, right? So you could slice like that, but you're going to get 1, 2, 3 separate integrals. Or you could do it the other way, still 3 integrals. Very unfortunate. A lot of work, super inconvenient. Nobody wants to do that. Okay, so what is this region anyway? I'm defining it in this example as being, let's see here, this thing is the image of the unit square. So I'm giving the unfortunate domain to you as an image. Now you won't always get that lucky, right? Very often the ugly domain that you have is not, you're not going to be handed, it's not going to be handed to you on a platter. Oh, this is the image. Here is how you do the pullback. Here's your new pullback domain. It's the unit square. It's not going to be immediate like that. So we're going to talk a little bit over the next several examples, most of which won't happen today, about how to figure out what is my pullback domain. Okay. But anyway, here it's the unit square. Now, image by what? What is this function? What is it that you do to the unit square to get this ugly green domain that we hate? And that's given to X and Y are these functions of U and V. All right. So the purpose of this example is to let's not worry about the complexities of in general, how would I find this change of variables function, or how would I figure out my pullback domain? I don't want to focus on that at the moment. I want to focus on, suppose that's all set up and given, how do I actually execute, how do I use the change of variables formula? Let's just get one done first, and then we'll talk about the harder aspects. Okay. All right. So here we go. Everything's set up and given. We know the first thing we're going to need to do is find our stretching factor, so we're going to have to look at this function and compute its Jacobian determinant. Right, this stretching factor is the absolute value of the Jacobian determinant. The Jacobian matrix is a bunch of partial derivatives. Y'all know how to compute those. Right, so you just have to compute the Jacobian matrix there. And take the determinant and take the absolute value. So our stretching factor is this right here. It's the absolute value of 4uv minus 9. Now this brings us to another awkwardness, and I'm going to go ahead and handle this awkwardness here. I think this is a good time to do it. What do I do with those absolute values? Right? Well, we don't want to leave the absolute values in there, because it's hard to do integrals when there's absolute values in there. I can't just erase them because they're there for a reason, right? That's part of the formula for how to compute area. I can't have this stretching factor be negative. Think about how ridiculous that would be. This area is what you get when you multiply this area times a negative number. That would mean one of the areas is negative. It makes no sense at all. It's completely unacceptable. Yeah? So how do we deal with the fact that these absolute values are there? The good news is, in this case, it's easy to figure out based on what we understand about our picture. Now, I have to zoom out to fit this all on, but 4uv minus 9. What can I understand about 4uv minus 9? Well, don't forget where u and v are. U and v are the coordinates of points in this box, in our unit square, because that's where our new domain is. What this says right here, we're going to be doing an integral on the new domain. That new domain is the unit square, the unit box, whatever you want to call it. And the u and v are very well understood on that box. U and v are both between 0 and 1. Right? So if u and v are known, right, when you can see it in the picture, that u and v are both between 0 and 1, then it's easy to figure out what to do with this expression. U and v are between 0 and 1, therefore their product's between 0 and 1. Therefore this term right there is never bigger than 4. And that means that when I subtract 9, this thing on the inside of the absolute values is always negative. All right, so I'm looking at the absolute value of an expression that is always negative. And the absolute value of a negative number is the negative of that number, right? It's just I know that high schools tend to be pretty bad about talking about absolute values, so let me just point out the absolute value of negative 3, for example, is the negative of that negative 3. Yeah? That makes sense to everybody? But it's nice to remember it in this way, that the absolute value of a negative is the negative of that negative. Okay. All right, so nice punchline then. The absolute value of 4uv minus 9 is 9 minus 4uv in this case. Now, what would happen if there's some ugly cases where, what if the thing on the inside is sometimes positive and sometimes negative? Well, then you'd have to take your domain. I mean, this would be a bummer, right? But what if my integrand, what if my stretching factor is, inside of the absolute value? What if it's positive over here and negative over here? Well, then you'd have to break up this new domain into pieces, and you'd have to do the integral on this piece with the positive of the determinant, positive times the determinant, and you'd have to do your integral on this piece. If that determinant's negative, then the absolute value is the negative of that negative, and so you'd have a negative sign. You'd have two different integrands off by a minus sign on these two different parts of the domain. So that might happen, and that's something you have to deal with. But very often it doesn't. In fact, we're going to find that there's a huge category of change of variables questions where that never happens. Right? So anyway, it's a possibility to be on the lookout for. In this case, no issue. Okay, so now let's just plug in. We'll call it a day after we're done with this example. Let's see here. There's our stretching factor. Stick that in there. Our dx dy on the integral that we were interested in now is Jacobian determinant times du dv. So there's our dx dy. Now, what do we do with the x and the y? Well, let's not forget where x and y come from. X and y, let's go back up to the picture. X and y are g of u and v. So the change of variables function itself tells you how to write down x and y in terms of u and v. So you can see it right here in this algebra. What is, let's see here, I'll use green. What is this x? Well, x is the first coordinate of the output. X is u squared plus 3v. There's x. What is y? Well, y is the second coordinate of the change of variables function. It is v squared plus 3u. So x plus y you can rewrite just by using the change of variables function itself. Everybody happy? And then it's all plugging in at that point. So we have this integral. This is a completely harmless looking integral. It's on a rectangle from where x and u and v go from 0 to 1, 0 to 1. Easy to write as an iterated integral. The integrand is a polynomial. Really easy integral. Punch it up. Okay, we'll pick up here next time. See y'all later. Oh, I do have homeworks to return.